welcome everybody. This is so cool. I mean, we had this afternoon event today where we actually were up at Lick Observatory where we had the dedication of the Milestone plaque up there. Just an amazing event. So this is just kind of a whirlwind day for me. But anyway, very happy to have everybody here. I have a lot of friends here, a lot of fellow IEEE members. How many IEEE people are here? Wow, that's pretty good. How many people either work at or work for a contractor to NASA, either to past or present? How many people have visited Lick Observatory in the past? Wow, that's a lot. How many people were there on August 1st when they measured the distance to the moon? Hey. So I think that's pretty cool. You know, it's a lot more than just measuring the distance to the moon. There's a lot of stuff behind that. And I think everybody's excited about it because so many of us were there on July 20th, 69, watching the TV with that little oval of Nixon in the corner, dealing with Nixon. But anyway, but it was such a cool event. So many of us remember that. Of course, there's a lot of people in the room who don't remember that. But I hope you get the vibes. I hope you get the excitement that comes with this, because it's really, I don't know, I'm pretty psyched about it. I think a lot of you guys are as well. So a friend of mine sent me this image. It's kind of interesting. Here's an East Africa footprint from 3.7 million years ago. I believe this is the oldest quasi-human looking footprint. I really don't know the story of it, but it's a cool image anyway. So I remember this. Remember when we always used to look at the newspapers to find out the news, or maybe the 6 o'clock news on TV or something like that? So I think a lot of us remember seeing like a newspaper headline about this when this came out. Now, how many people have seen 2001? How many people saw it back in the day? How many people saw it on Cinerama with 3 projectors? Woo! I found out that it was actually playing at the LA Cinerama Theater for 103 weeks. Now think about that. One movie, one theater, 103 weeks. That doesn't... A lot. Anyway, so it's kind of insane. But if you look on the right, it was also playing in San Francisco at the Golden Gate Theater, which is now used for live theater. Back then, it was a Cinerama Theater. I saw How the West Was Won there. I saw actually 2001 at the LA Cinerama Theater. But anyway, so here's a little thing that came out right around the time of the Apollo 11. You know, a special, like it had already been playing for a year in San Francisco at the Cinerama Theater. And here's a little thing with regard to the Apollo 11 landing. So I think that's emblematic of the excitement of the time. You know, 2001, all this cool stuff, and landing on the moon. So I think that's kind of, to me, that's really emblematic of that whole time in that place. So I'd like to thank a lot of people who've been involved in this with me. Texas Instruments has provided this beautiful building and our staff in the back, so thanks very much. And we've got a lot of volunteers, people checking you in and doing other stuff to make all this happen mainly from the IEEE Santa Clara Valley section, and a lot of those people are sitting right here near the front. So thank you very much to all you people for your help. Thanks to the IEEE Foundation for its support of this event as well. Now, Vioti, there's a friend of mine, Ken Pyle, back in the back there. He makes videos of a lot of these events, so we've got a lot of them from past events from like the Tech History Committee, and also Ken is a great guy, so you might see him running around with that camera and stuff, so thanks very much to him. Thanks also to Mustafa Murtadsai for his help, because he's kind of been my PR guy. He's contacted the local TV stations and all. Unfortunately, there's a big event down in Gilroy after the shooting down there, so otherwise we may very well have had some of the networks here covering this event tonight. We did get, because of him, we got proclamations from our Congressman Ro Khanna, from our Congresswoman Anna Eshoo, and also the mayor from Santa Clara. We all have declarations from them, or proclamations for this event tonight, so I thought that's pretty cool. So thanks very much to Mustafa here in the front row. Also, she can't be here today, but Eleanor Gates, the staff astronomer, was my main contact at Lick for these events. I got a picture of her. You can see the enthusiastic look on her face. She's just this bubbly woman who's a staff astronomer there who's been great to work with. So anyway, thanks to her, even though she can't be here tonight. So, who's a Big Bang Theory fan? We're going to do a little clip from that. I'm not sure if you've seen this, but it relates to tonight very much. So if you could play that clip, please. Our first speaker tonight is Stan Retief. Stan has held senior level positions at many, major human services organizations in the Philadelphia area, including as Vice President of Development and Communications at Wood Services. He currently serves as Chief Development Officer at the IEEE Foundation, and we can thank him and the Foundation for the support of this event. How many Foundation donors do we have in the audience, by the way? Great, happy to have you guys here. Please welcome Stan Retief.
Thanks very much. Today has been quite a wonderful opportunity for us and quite a day, and we want to thank all of you for being here. I have a brief presentation for you, but I really think the more important thing is that we get through this so that you can hear more from Dr. Walker and some of the others that you're going to be hearing from, because that was quite intriguing this afternoon. We're looking forward to hearing more. But the IEEE Foundation is, actually there's a connection to home, your home, because our president is one of your neighbors, John Treichler. I believe he's even a member of your section. John is the president of the IEEE Foundation. He's not with us tonight. He's on the East Coast, much to his dismay. But he does a great job for us representing the foundation and the programming that we serve. The programs are all things that are done basically as IEEE's philanthropic partner, but they're things that are done in the name of our volunteers, in the name of our members. And that's slow. But they're basically a couple of different things that we try to hit. Illuminate the possibilities, educate the next generation, engage a wider audience, energize innovation. So everything sort of fits in those very broad categories. But the most important thing about the foundation is that all the programming that we do are basically done in the name of our members. And so I think that that's a very interesting and very important part that you should know about the foundation and what we do. Of all of our programs, the History Center is probably our most popular, to be honest. Whenever we do a survey, History Center always is coming toward the top. And I know that the Milestones program in particular is very important. And we thank Mike Gaselowitz and his staff for the partnership that we enjoy with them. One of the things we're trying to do is raise awareness, raise more donors so that more people are raising their hand when we talk about who's supporting the foundation, and of course raise some money to do those programs. Our goal for this campaign, the first in the history of the foundation, is $30 million. And the good news is, to date, we've raised over $20 million, and we've got the better part of a year and a half to go. So we're looking forward to having a successful conclusion to that. Just a few people I'd like to thank who are very important to us and to the work that we do. First of all, the Jeffries, Jim and Gloria Jeffries, we appreciate their participation tonight, the time and the talent that they've lent us, not only today but over the years, and that's much appreciated. So if you wouldn't mind. May I say that we do a lot of these types of events. The section leadership is outstanding, and the volunteers and the nice spread, but really the welcome that we got when we walked in, you should really give yourselves a hand. So that was very nice as well. Danny DeLiberato from our foundation staff who's helped put this together. But Brian Berg, I mean, I know for you this is a labor of love, and we appreciate the energy and the effort that you put into this. Jim Jeffries mentioned earlier today that this is the 198th milestone, and I believe, and correct me if I'm wrong, if I'm wrong, it's not he wasn't wrong, I'm wrong. But it was, I think there are 17 from this section.
There's 17 from this section, I think 26 in Region 6.
Okay. Okay, so 17, that's almost 10%. Brian's telling me earlier that he has participated in about 9 or 11 of those, and that he has brought to completion 4 of them. So obviously it's a labor of love, and we thank Brian for his efforts in that regard. Yes. What I said to you earlier is that the foundation supports programs that are done in your name. What's happening tonight, we're celebrating the successes and the accomplishments that are done in your name. So congratulations and thanks very much. Enjoy the evening.
All right, thanks very much, Stan. Our next speaker is Michael Bolt. Michael is a distinguished professor of astronomy and astrophysics at UC Santa Cruz. And by the way, Lick Observatory is part of the UC Santa Cruz Observatories. So it's actually part of the University of California Observatories, but it's closely aligned with the University of Santa Cruz. Michael received his doctorate from the University of Washington and received a Plaskett Prize postdoctoral fellowship at the National Resource Council of Canada, then became one of the first NASA Hubble Prize postdoctoral fellows. He joined the faculty at UC Santa Cruz in 1993 and was director of the UC Observatories from 2005 to 12. Please welcome Michael Bolt.
Thank you very much. It's really wonderful to stand in front of an enthusiastic audience about one of the accomplishments at Lick Observatory. He didn't tell me everything I needed to know about this thing. No, okay, I just pushed the button. So, thank you very much for being here. I'm just going to quickly give a little bit of context for the lyrics experiment by telling you what Lick Observatory is. The University of California, instead of having a 14-inch telescope on the top of every physics building, they've always combined their, now it's 10 campus resources, to have state-of-the-art observatories. So that was Lick Observatory for 100 years. Now, Lick Observatory, as I'll tell you in a second, still plays a really important role for the University of California. We're also part owners with Caltech and NASA of the two Keck 10-meter telescopes on Mauna Kea in Hawaii. So, University of California Observatories is headquartered in Santa Cruz, that's that connection. And we operate Lick Observatory on behalf of all the University of California. We operate our part of the Keck Observatory. And we also have instrument labs in Santa Cruz and UCLA that build the very sophisticated instruments that make astronomical telescopes so powerful. So, the start of Lick Observatory is a very interesting story. I could talk for an hour about this and you'd all be amused and enlightened, but I won't because I only have 5 minutes. James Lick was a wealthy fellow. He made his land and his money, in real estate in the San Francisco area and beyond. He made a really outstanding gift back in the 1870s of $700,000 to build the finest observatory in the history of mankind. It's a pretty nice thing to be able to do with your legacy, I think. The observatory was completed in 1888. It was the first time an observatory had been built on a mountaintop. Often up until that point, they simply built them somewhere convenient. The back 40 acres of the Harvard campus or downtown Cincinnati. Okay, there are many advantages to being on a mountaintop. The disadvantage seen then was it was remote. So it was also the first permanently occupied observatory. So this kicked off a trend in observatories that has continued to this day. And when it was completed, not exactly the first day, but certainly by the time the 36-inch refractor was installed, it was the premier astronomical observatory in the world, which means in the known universe and the history of the known universe. Okay, so they did many things back then. Not only did they have an excellent sight and a superb telescope, the 36-inch refractor is what you're seeing here, but it was one of the places that, and this has been a story at Lick Observatory ever since, they were at the forefront of technology innovation. And what that meant back in the late 1800s was they were quick to adopt photographic plates as a medium. So up until that time, people looked through the telescope, made a little sketch of what they saw, had a drink of coffee, and about 3 a.m., things looked like they'd had a lot of coffee, I suspect. But photographic plates allowed you to record things with much higher fidelity than your eye and your hand. But even more importantly, they could, if your telescope tracked the sky properly, you could make longer exposures. In fact, you could expose as long as you could have the telescope accurately track the sky and see much fainter things or collect higher fidelity data on a given object. You could take spectra. So they did a lot of stuff. They mapped the Milky Way photographically. They discovered all the dark areas, which were a point of very mysterious back at that time. Lots of comets were discovered because they were recording the sky so accurately and to faint magnitudes. And these last two bullets are important. They measure the motions of stars. If you look up, everybody sees the reflection of the Earth's rotation. The sky appears to move from the east to the west. But in fact, all the stars in our galaxy also have so-called proper motions, independent motions, along the line of sight in the plane of the sky. And if you can take accurate enough data, you can map the motions of stars. So this was one of the major activities at Lick Observatory. And they could also take spectra of individual stars and measure the motion of one star around another and use the physics that was well understood by that time to start to really do astrophysics. You could measure the masses of stars, you could measure dynamical properties of stars moving in the galaxy. So this was, in my view, really the birth of astrophysics back in those days. An important thing happened in the 1895. So you can use a big lens to collect the light, your telescope, to send to your instruments. The problem with lenses is the light has to go through them, so you can only support them on the perimeter. So as a piece as a lens, which is typically made of glass, gets larger and larger in diameter, its self-deformations start to become big enough that you can't make good images anymore because you can only support them on the perimeter. The wonderful thing about mirrors is you can support them on the back because the light bounces off the front. So I think one of the first really scientifically productive telescopes that used a reflecting mirror was this Crosley. In fact, with the Crosley telescope, they took very deep exposures of the sky. They were interested in things like the Andromeda Nebula, and they realized that the universe is full of these fuzzy things that don't have the same distribution as stars in our galaxy. And this was critical material in the 1920s for the huge and very important debate about whether our galaxy of stars that the Earth is part of and our sun was the only. That was the universe, was our galaxy, or were there many other so-called island universes like it out there? And some of the early data taken with the Crosley were crucial for settling that debate. And of course the answer was, we're, like it or not, we're just one galaxy among trillions out there. So that's one of the big discoveries at Lick Observatory. Okay, William Campbell was the director and the president of the University of California for many years. And he said, what's the most important thing we can do in science is to verify or refute Einstein's theory of general relativity. And even though the story is that Eddington immediately used an eclipse to demonstrate that. In fact, Eddington's data were not conclusive in the end. So Lick Observatory started this long observational program traveling to eclipses all over the world to measure the so-called deflection of starlight around the limb of the sun. And in fact, I think that the Lick data were the ones that definitively demonstrated that Einstein was right with his theory of general relativity. So there's a picture of Campbell as the second from the left in the photo standing next to Einstein. Okay, so 1958, I sort of think of that as the modern era. Lick Observatory had fallen behind the observatories in Southern California. But this big dome in the front of the photograph is the 3-meter telescope, the 120-inch telescope, which at the time it was built, it was the second largest in the world, and remained so for 18 years. That's where the laser that almost blew up the moon was shot from. And this sort of gave Lick Observatory a second life as a forefront research place. In 1969 is an important point here that we'll hear more about tonight. So we've used the observatories up there and their proximity to the labs in Santa Cruz to do lots of technology development. This is the first observatory that routinely used adaptive optics, where we take the motion of the atmosphere with some very fast, very sophisticated optoelectronic systems. We measure the blurring caused by the atmosphere, and we eliminate it with deformable mirrors. We still use observatories, we still use telescopes up there every night. It's the fact that we can operate most of them remotely or even robotically has really helped with that. Okay, one more discovery. So we started a program in sort of the modern era, in the 50s, where we measured the sky twice, or 3 times, or 4 times in some cases, very accurately, to measure the motions of all the stars. When they removed the objects that apparently changed their position in the sky, had a proper motion over a decade or 20 years, everything left over, all the background, those were these galaxies, the extragalactic galaxies. And this picture here is a representation of the counts of galaxies that was made first by Lick Observatory data and Lick Observatory astronomers. And there was the first indication that the universe wasn't uniform at all, but instead galaxies were distributed in this very, very interesting way, which is really the foundation of modern cosmology. Any theory you have for the development of structure in the universe better look like this at the end. Okay, here we go. So we still do this. In 2019, we still do lots of stuff up there. The first planet orbiting a star other than the sun, the first exoplanet, was discovered by our colleagues in Europe. But out of the next 100, 82 were discovered with the 3-meter telescope. This became one of our particularly important cottage industries. This has been a terrific new branch of science, basically. And Lick Observatory has played a really big role in that. We do lots of technology development up there, as I said. It's really easy to develop things in the labs in Santa Cruz and go test them out up there before we move them to Keck or some other place. We do lots of undergraduate and graduate education, and I'm particularly proud of our terrific public outreach program up there. So every year we have many, many visitors. We have programs during the summer. Our June programs, the tickets go on sale in April and they sell out sometimes in an hour. It's just amazing how popular this place is. Okay, so it's been a wonderful place. Lick Observatory, it's 130 years old. The scientific breakthroughs, the technology development, training of students, and bringing all this to the public is, I think all of us associated with Lick Observatory are really proud of this. But I have to say that when somebody says, oh, you used to be the director of Lick Observatory, tell me a good story. My favorite one by far is the time we shot that laser on stun at the moon. So I'm proud of this. Thank you.
Thanks a lot, Michael. By the way, when I was thanking people, I forgot to thank my wife. She's in the back, and she checked about a third of you in tonight, so thanks, Joyce. So our next speaker is Dennis Wingo. I know Dennis by way of the Silomar Microcomputer Workshop. Who has attended a Silomar? Hey, we got a number of people here. Great. I've been on the committee for a number of years and made a lot of connections that way, and made a connection here with Dennis. And in fact, Dennis was found by one of the key members of the committee, John Wharton, who unfortunately passed away last year. But very nice to have Dennis with us. And so John Wharton is with us in spirit by way of you, Dennis. Yes. So Dennis is CEO and founder of SkyCorp and also Green Trail Energy, Inc. He's also co-founder and CTO of Orbital Recovery. He has extensive skills in solar electric propulsion, satellite and spacecraft design, advanced mission planning, and lunar surface operational scenario development. You can read his bio in your program, but one topic that I did not include there was the fact that Dennis restored and digitized the images of NASA's Lunar Orbiter program. And that's a whole interesting story unto itself. I also appreciate the fact that Dennis is connected with me with Seth Shostak, who will be our interviewer tonight of Dr. Walker. And please welcome Dennis to the stage.
Well, thanks, folks, very, very much for having me here. I look out on the gray hairs here, and I wonder which of you I might have worked with in the 1980s in the computer industry up here as well as in Southern California. I want to thank all the old guys who helped bring us along and who helped mentor a lot of us young folks back in that era. So thanks very much. The time is now. Neil and Buzz landed on the moon in July of 1969. The last was my friend Harrison Schmitt in 1972. Who's upset that we haven't been back? All right, I agree. And my very first public speaking was in 1989 when it was 20 years after, and I was at this big NASA event, and I'm listening to them talking about going back to the moon, and it finally upset me so much, I got up and I asked the first question. I said, when are you people going to quit talking about it and let's go back to the moon? So that's the way I still feel today, and so I've dedicated my professional career since the 1980s in working with the moon. And so there is a lot of stuff that has happened since the 1980s in remote sensing of the moon. We know so much more. We know about the water. We know about the remote sensing that has confirmed many, many things about the moon that we didn't know before. So our goal is actually, and I work very closely with a lot of folks at NASA, NASA JSC, NASA headquarters, NASA Langley, NASA Ames. Our goal is actually the industrial development of the moon. And here at Texas Instruments, a lot of you folks work with vacuum manufacturing, chemical vapor deposition, and vacuum. These are some of the technologies that we hope to bring to the moon. And with our remote sensing missions that we've had and the discovery, and let's call it confirmation in 2009 of billions of tons of water on the moon, we now have a lot of, let's call it the fundamentals for us to go back to the moon in force. But a lot of other tech that has been developed, like 3D printing, different additive manufacturing technologies, robotics, AI, machine learning, swarm robotics, all of this is going to take us back to the moon. This right here is my favorite area of the moon right now. NASA's talking about going to the South Pole, but this is the North Pole of the moon, where it's much more tractable for robotics, and we've done a lot of work in this. This is a times 10 exaggeration of Whipple, which is one of the crater next to the North Pole and one of the areas of permanent light on the moon, or near permanent light, about 89% sunshine. So we can do this with solar power. We don't have to wait for nuclear power. I did a design study just a few years ago showing with 1 megawatt of power, we get about 670 kilowatts average power a month, and that is plenty for us to begin the task of industrialization. This is the Whipple site details. It's the edge of a crater, and we know from the orbital missions, the Lunar Reconnaissance Orbiter that's there now, that this is the area that has the maximum light. There's a really cool program called Moon Trek. It's developed here at NASA Ames that allows us to do a lot of mission planning and a lot of surface operations. Let's call it preparation, which we're still doing now. So the steps. This is not a science development. We are not going to the moon to recreate the Antarctica Research Station on the moon. We're going to use the moon, and we're going to industrialize the moon to build things, to do things that help us get to Mars. And as I say, I wrote a book about this in 2004. We go to Mars to take our civilization there. We go to the moon to help save our civilization here with new technologies, new approaches that can be fed back into the terrestrial science and engineering communities for us to be able to make the move forward. A little bit about lunar industrialization. This is a design I did for NASA in 2006. These are what's called power towers. Each one of these are 100 kilowatts. And I just talked to IEEE today, and we're going to be making a very concerted effort to work with the professional societies, IEEE, ASME, ASCE. I'm a concrete canoe guy in college, to develop standards for lunar surface systems operations and the things that we need to operate on the moon. Power, so there's a power, the 100 kilowatt power towers, adding capability with swarm robotics, metals processing, forging, pouring, all of the things that we've done to industrialize the Earth. Different and versatile robotics, gantry clearings, all the stuff we use here on Earth, we translate it for use on the moon for an industrial development. High mobility rovers or other things. So a lot of the stuff that originated here with self-driving cars is going to have direct application for the moon. So 3D printing, everybody knows what that's doing now, the metals printing. And just think if you have a 10 to the minus 12 torr vacuum to where you don't have the contamination problems that you have here in any of your vacuum manufacturing on Earth, that's the kind of quality vacuum we're going to have on the moon to do a lot of stuff. laser sintering. So this is kind of what it might look like. We're pouring metal, and one of the things that we're working with Seth's group at, we're doing a thing called the Frontier Development Labs, and one of our projects, it's being hosted by SETI this summer, is that we're looking for metal meteorites. 3 or 4 out of every 100 of those holes on the moon were done by a metal meteorite. And we're looking for these material resources to jumpstart lunar industrialization, and these are some of the fun things that we do with our friends at SETI and here at NASA Ames in Silicon Valley. Thank you very much.
Thanks very much, Dennis. Always fun to hear you talk. Our next speaker is Jim Jeffries. Jim was the 2018 IEEE President and CEO. He's a retired AT&T and Lucent Technologies executive who in 33 years rose from manufacturing engineer to vice president. He worked directly with the Bell Labs teams that developed fiber optic cables and also served as a logistics vice president responsible for worldwide supply chains, quality assurance, and export planning. I had the pleasure of having Jim officiate at a IEEE Milestone dedication for Shaky the Robot about 2.5 years ago at the Computer History Museum. Who was there at that event? Excellent. That was a really fun event. We had like about 10 people from the team that had built this first mobile intelligent robot that's had an impact on the world, including Google Maps. Any kind of mapping techniques you use right now has its basis in what was developed from Shaky the Robot. Really interesting stuff. So, glad to have you here, Jim. Take it away.
So thank you. I wanted to talk briefly tonight about the legacy of history at IEEE, since we're celebrating historic events. Before I do that, I just wanted to talk about IEEE just for a minute. You know, IEEE today, for those of you that may not know IEEE, is the world's largest technical professional organization. Our mission is advancing technology for humanity. And we do this through our members. IEEE is a volunteer-led, staff-supported organization. And we do this through our members who are engaged in learning, they're engaged in teaching, they're engaged in practicing, they're engaged in innovating, and they're engaged in advocating for technology. Now, today's IEEE is defined by a great geographic reach, 400,000 members all around the world, by technical breadth in the many societies, leading journals, publications, and conferences, and standards. It's also defined by increasing social impact in public policy, humanitarian activities, the development of ethics, so much importance is growing in that today, and also the continuing education of our members. I want to return to the history for just a minute. You know, IEEE's legacy goes back to this story of innovation that goes back to 1884, when Edison and Alexander Graham Bell and some others responded to an ad in a trade publication in New York City and decided to form the American Institute of Electrical Engineers. They were concerned about this nascent profession called electrical engineering, and they were concerned about how power was going to be possibly deployed to an entire country and how communications might happen for a whole population in the United States. These were the things that drove them to come together. So they formed the Institute, and the American Institute of Electrical Engineers. In 1912, the radio engineers did a similar thing. So the Institute of Radio Engineers was formed in 1912. The next big step was, well, now we can connect the whole world together with wireless communications. And those two groups fostered, continued to be a part of the history of technology. And then in 1963, 56 years ago, IEEE was formed by the merger of those two organizations. So IEEE has always had a strong legacy in history. What are the benefits of preserving history? Well, I think there are a lot of benefits in preserving the history. It certainly goes to increasing the public understanding of the impact that engineers and scientists have, both on daily life and the total advancement of society. It also goes to the importance associated with image of the profession, growing the strength of the profession, encouraging people to become part of the profession and growing forward. And it also enhances the images and preserves so many things. So if we have a legacy in history at IEEE, there's a good reason to preserve history. What can a professional society like IEEE do about that? Well, we have an IEEE History Center. You've already heard it mentioned this morning. The History Center is funded by our IEEE Foundation and is fully staffed and permanent. And in our History Center, we basically have this mission of preserving, researching, and promoting the history of technology. We do that through a number of different ways. We have staff historians on site. We partner with Stevens Institute of Technology, where the History Center is located, and do all the things that are listed here: oral histories, collecting of information, archiving of documents. And we also have the Engineering, Technology, and History Wiki, ethw.org, where you can see many documented stories about the history of technology. And we do that not just by ourselves, we do it in conjunction. You heard just a minute ago about other societies. We have included in there the mechanical engineers, the chemical engineers, the civil engineers, Women in Engineering, Society of Women Engineers, the mining engineers, the petroleum engineers, in a consortium. And so we're very focused on preserving history and keeping that going. We also keep the archives of IEEE. It's very interesting to go to the basement of our headquarters building in Piscataway, New Jersey, and maybe you can ask the historian there to open up the logbook where you can see Edison's signature as member number 234. And it looks like he paid his dues on time, as near as I can tell. So we have this incredible archives, incredible growth of a history wiki going on, and this is what we're really all about in our History Center. We also do a milestone program. We're celebrating one tonight. As mentioned earlier, number 198. The milestone program began in 1983 as part of IEEE's centennial year, our own 100th birthday at IEEE. And since that time, in that 35-year period, we've dedicated 198 milestones. They span more than 3 centuries of technological progress, beginning with Benjamin Franklin's experiments in electricity in 1751, all the way up through 20th century achievements. And we continue to grow the number that is out there. So milestones give us this chance to mark the path of progress and to, again, do all the things that preserving technology and preserving history can help with. We also sometimes do special programs. This year we are doing a special program commemorating the human space travel. Obviously this is the 50th anniversary of the Apollo landings, so human space travel in a bigger context, a special resource here to collect information from our members who have been a part of that. Oral stories, any artifacts that are appropriate, and of course these 2 milestones, including the one we'll celebrate tonight, and papers and things. So we continue to work on special projects. We also have an IEEE REACH program. You know, the IEEE REACH program stands for Realizing Engineering Through the Conduit of History. And this is a series of programs that we put together that are designed for late middle school and high school students to talk about the history of technology, lesson plans for teachers, support games and programs that can be operated, as well as support materials, with the goal of introducing the next generation, to the opportunities that might exist for a STEM education and a STEM career. So these are the kinds of things that the History Center can do. And of course, we can all get involved here. We can certainly propose and develop milestones. I mentioned IEEE is very much volunteer-led. Our volunteers are the ones who identify the milestones, nominate the milestones, provide the documentation to support the milestone, run it through the History Committee that reports directly to our Board of Directors and can lead up to this excellent documenting of the long-term impact of history. We can also do a selfie. You can post a selfie to anytime you go by a milestone plaque. If you want to take a selfie, we have an address. You can send it in. We'll be glad to put it up on the website. And you can look through those. So you can do a selfie. You can also contribute your story to the Engineering, Technology, and History Wiki. If you look at that site, it has a lot of information on it, and it's just fun to kind of go through and just hit things that might be of interest to you. And finally, you can support the IEEE Foundation, which funds much of our historic work. So that's a connection between IEEE and history, and we're proud to support the Milestones program and glad to be a part of this evening's event. Thank you.
So I'm going to do a quick run through of the milestones that are in this immediate area, and I'm going to do this quickly because we want to get to our main program here. So just let you know about a few of them. Over on San Antonio Road by California Avenue near El Camino, there's actually 2 milestones, and they're very easily accessible because probably a lot of you have driven by them quite often, maybe didn't even notice. One of them is birthplace of Silicon Valley, which is where Shockley Labs originated, and also Moore's Law, which is on the other side. There's a beautiful fountain with a silicon crystal module in the middle of the fountain. And then The Ampex video tape recorder was an IEEE milestone included in the pictures. Second from the left is Ray Dolby, was one of the developers of that. The Raymac disk drive was invented in downtown San Jose in 1956. And SLAC, the Stanford Linear Accelerator Center, was honored. Also, the inception of the ARPANET, which was the first transmission from UCLA to SRI on October 29th, 1969. So coming right up is the 50th anniversary of the ARPANET. Also, the integrated circuit, particularly the planar architecture for that integrated circuit at Fairchild. And the demo, often called the Motherwell demos of Doug Engelbart's up in San Francisco. And the CPM operating system developed by Gary Kildall down in Pacific Grove. And the Dialog online search system, this was a milestone that I was involved with that was dedicated 3 months ago. It's developed at Lockheed Labs and precedes modern search engine by over 2 decades. Really interesting product. And the Computer History Museum itself has a plaque. It's called a special citation because it's a museum, and there's a set of plaques on a wall there. I started the process of adding plaques that are duplicates of ones that are in other historically significant locations. So if you go to the History Museum, you'll see a bunch of IEEE milestone plaques there, and that number will be growing. So on to the main part of the evening. Very happy to be able to introduce the 2 people who will be participating. We are welcoming Seth Shostak. He'll be performing an onstage interview. Seth is the senior astronomer and fellow at the SETI Institute in Mountain View. He's conducted radio astronomy research on galaxies for much of his career, and he's written over 500 articles and web stories on topics in astronomy, technology, film, and television. Seth chaired the International Academy of Astronautics SETI Permanent Committee for a decade, and he hosts SETI's weekly hour-long science radio show titled Big Picture Science. He'll be interviewing Professor Hildreth Hal Walker, Jr., and he'll be in conversation with him here on the stage. Hal installed the radar systems in fighter planes during the Korean War, worked on the ballistic missile early warning system, and also worked on the first satellite-based TV transmission in 1962. He later joined CORAD, where he led the manufacturing, testing, and operation of the Ruby laser system in the Apollo 11 experiment that we'll be celebrating tonight. He's also the guy who actually fired the laser multiple times before it actually hit pay dirt exactly 50 years ago tonight. Hal is here with his wife, Dr. Betty Walker, and she has her own interesting story as a pioneer of STEM education and outreach. She's with us here in the front row, and I have a feeling that Hal just might talk about her during part of our conversation. So let's welcome Seth and Hal to the stage.
Let me introduce my wife here. She'll be helping me with this presentation. Thank you, Dr. Betty Walker. Raise your hand out there. And if I say something wrong, she'll very quickly let you know I did. Okay, all right. Okay. Well, I want to start out by saying how lovely and wonderful it is to be here at this IEEE time in this celebration. As we all know, 50 years ago, many of us gathered there at Lick Observatory to attempt the first laser ranging experiment with the accuracy we had anticipated. Because, of course, we were not the first people to fire a laser to the moon. Many other research institutes had fired lasers previously, and of course, that light was very random reflections and so forth, so the accuracy of that was suspect. Now, what we wanted to do, of course, with my life, I want to start by saying my involvement started out as a young boy. I grew up in the South. I was born, I think for everybody's information or Milestone, I was born in 1933 in New Orleans, Louisiana. So, of course, in those years, things like lasers or going to the moon were not even a topic. But there was Buck Rogers. I started reading Buck Rogers magazines as soon as I could count to 10. Okay. But here's what happened that was so important in my career. My dad, when I was 8 years old, of course, we might remember, many of us back in the day, Daisy air rifles were quite popular. So, of course, when I got old enough to get a rifle, or some type of a weapon, I asked my dad for a Daisy pump rifle. And, of course, I was all excited about that. He said, yeah. But then when I went to him to get the gift, it was in a brown bag about yay big. Today they would probably call it cocaine, but it was about that, something like that. So I was very disappointed. I mean, to have a Daisy BB gun you were like the top guy on the block. I reached in and pulled it out. It was a Buck Rogers ray gun. And I've always mentioned this when I talk about my life story, that you have to be very careful what you put in a child's hand. Because when I pulled the trigger, there wasn't BBs coming out, it was little sparks. And I always want to say I followed those sparks all my life. And it took me to Apollo 11 with the biggest laser in the world at that time. The type of laser that we were operating there, and I always want to mention this because we were using a weapons-grade laser. I want to say that very quietly, weapons-grade laser. Because in those days, if you mentioned something like that, people got excited. Because again, the beam and the ray was sort of like, how much damage can you do with a thing like this? So of course, my friend, the inventor of the laser, Ted Mayman, we all got to be friends, is working at Corad Lasers in early 1960s. Ted, when asked about this problem of the laser, said, well, look, the laser is a solution looking for a problem. Well, of course, his management at Hughes Aircraft Company's research labs thought this was a wonderful idea, the laser. Let's go down and take a look at it, Ted. So when they went down to the lab and Ted finally went, what are we going to do with that? So, of course, Ted got very ticked off, make a long story short, and retired from Hughes Aircraft Company. Started his own company called Corad Lasers. And for all of you all here tonight that have read that word in some of the write-ups you've seen, you probably want to know what CORAD means. It means coherent radiation. Okay, yeah, okay, that's what that is. So anytime in the future, you'll be an expert now on CORAD. But that company started to bring together just talented individuals from across the spectrum, electronics, physics, you name it, cooling systems, so forth and so on. And our first job, of course, was to start to get involved in scientific research programs with a small laser that did about 1 joule. This laser was pumped with 5,000 joules of an input, Ruby pulse laser, 6943 angstrom output. And of course, this was used quite extensively around the country. My role at that time at Corad was I was the field operations manager for Corad and also ran the manufacturing department for Corad's laser manufacturing. Because again, we felt that the person that knew how to build it should go operate it, because at that time, no one was really that familiar with it, because most of our researchers were guys that stood around scratching their heads about what was wrong. So the guys that built these things got to be the experts. I was known at one time, I guess we've probably been roughly around, I'd say 67 or so, I'd probably fired more laser shots than anybody on the planet. Because again, I fired lasers every day, all day. That was my job. Now, that leads us again to why I was one of the guys that ended up at Lick Observatory. No one in the world had fired more laser shots than me, and maybe some guys could have tried to know about them. But at that time, that was my reputation. I won't go to what they called me, but anyway, yeah, that was one of the things I took credit for. But again, the laser at Lick very quickly was a K1500. You've heard us describe it and read about it. It was a multi-stage device using synthetic ruby crystals. It was a 2-stage unit that an oscillator had developed about 1 joule or so on the output of that. And of course, it had an amplifier that had a 10-inch, half-inch crystal inside the amplifier. We pumped that section with 25,000 joules. Now you might say, why were we putting that much power input to a laser that could only get out about 12 joules? Well, ruby was one of the most inefficient mediums that was around in those days. That's why we had to go to YAG and neodymium later on in years. But again, we brought that type of a laser here to Lick, and prior to that, I was mentioned earlier, was a weaponized system. We developed it for Kirtland Air Force Base using some of their research there. I'm sure you know what I mean. But once the mission to the moon was developed by some very nice guys, one of them sitting right here in the front row, raise your hand, Joe. and Dr. Fowler, who's not here with us tonight, I understand he's overseas. But I always say to my audience when I speak that other people came up with the idea to do this. I was busy doing a lot of other things. And of course, when the suggestion was made that we would use a laser to do a ranging experiment, now who else would they ask but me to come and do it for them? So I said, great, I'll do that for you. So I pulled together a team, and we built 3 lasers over the past, leading up to Apollo 11. 3 lasers were built, primarily for doing one from Haleakala, classified work, which I'll describe was basically blinding Soviet satellites. That was interesting. We had a lot of fun doing that until they figured out how to stop it. But anyway, that was another story. But when it came time to go to the moon, we said, well, wait a minute. Joe and the guy said, wait a minute, if the laser reflector is put down in a certain place and maybe dust and other things get on it, so forth and so on, all these problems may come up. We got to try to find this thing. So, of course, we scratched our heads and talked about it and chose to use this K1500 as the acquisition laser. And I want to make one thing sort of to everybody's knowledge. Our job at Lick Observatory was just to find the reflector. We were on a search mission. We were not there to necessarily find out how far away the moon was or to find out what the benefits of laser ranging, none of that. My job was to run a laser that had satisfactory power to reach the moon, search for the reflector, which in case, as we know from one of the discussions earlier, they did not quite land where they anticipated. Now, we had characterized the surface area around the Hopi and Sea of Tranquility, that base, where the base would happen, for some weeks leading up to it. So when Neil Armstrong took control, I was sitting there watching him on screen. I said, oh my goodness, look what he's doing. He's flying away somewhere. Where'd he go? so I said, let's start looking for him. And of course, that was our next mission now, go and actually find where the reflector was located. In the meantime, I had a second laser we had built at CORAD that was being, I think we'll see it in a film, in a slide later. It was a much more powerful laser than the one I had, but its purpose was it could develop more pulses per minute than we could. We could only fire 1 shot per minute. 1 gigawatt, 12 joules, 10 nanoseconds was the pulse length. And so therefore, to us, that was about the extreme of what we could produce. However, the lasers we built at McDonnell were able to run at much higher repetition rates and so forth. So that was my colleague there operating that laser, Jim Myers. And I want to mention his name tonight because many of these gentlemen that were working very extensively in this program are now deceased. It's been a long time. I just thank God that I'm still here to talk about it a little bit. But Irv Weiner, again, as many of us know here at Lick, was a very prime participant in that activity there. We want to mention him. He's deceased now. And of course, Jim Myers was operating the laser at McDonnell Observatory. And of course, another colleague of mine, Bill Rundle, was operating a laser from Haleakala that was in a classified state that I don't necessarily talk that much about. But that was kind of what made up the American presence for the Operation Lure in 1969. Okay, sort of an introduction.
Terrific.
Yes.
All right, I'll turn on this feedback device.
Okay.
All right, well, we have plenty of time here, so I'm going to go through some of these questions here that Brian asked, but, maybe for historical purposes, with what accuracy, when you finally got around to measuring the distance of that corner reflector on the moon, to begin with, you're not going to get a whole lot of photons back, even with your 12 joule laser. How many photons would you get back typically?
Well, I think we were looking for like 3 to 5.
3 to 5, okay.
5 or 6, something like that. 4, maybe 4. 3.
4, say 4. And getting far more infrared photons here in this room.
Doing our talk like this, I'll try to interrupt our for futile pointers. One of the things that happened after we had got operating, because again, you just imagine, most of our technical institutions all across America had participated in some degree to build a device or apparatus that could be used as part of this system. The laser was just the source. In the meantime, MIT built the receivers and somebody else did something else over here. So we unfortunately damaged the MIT receiver after about a couple of days. And of course, now what do we got to do? Cold War problem pops up. Call comes. Hey guys, the Russians are lasing on the moon, and if they find the reflector before we do, who's going to be responsible for the $35 billion we spent to get there? Not me. Okay.
So there was an aspect of the moon race
Yes.
that you were involved with. Now, I mean, those astronauts took 4 days to get to the moon. You took about 1.5 seconds. That's clearly an improvement. What were the Russians doing? I mean, how far did they get? They didn't beat you.
Well, they actually landed, I think this is true, I've read it someplace, they actually landed Lucanoid 1 or 2 a day before we got there, I think.
They had a reflector.
Anyone can say a yay or nay? 3 days before Apollo 11 landed, the Russians landed a French-Russian thing that had a mirror on it, whatever it was, I never saw it personally, but they got into a ditch, we'll call it, and couldn't get their reflector to look back in the right direction. But we did find it for them later and told them where it was, but that's another story.
I'm sure they were grateful. Okay, so you finally fire this thing up. You send a lot of pulses. I assume you're just averaging all the returns so that
Yes.
you're only getting a couple of photons, right? So you build up the signal noise. Now, the distance to the moon, I mean, that was a project that interested the Greeks about 1,200 years ago, and they did it too, but without lasers. They couldn't afford them. But they did measure them, just the curvature of the shadows during eclipses. And that got a number that was right to within a factor of 2. And as Mike Bolte will tell you, in astronomy, a factor of 2 is pretty good accuracy. But by the 1950s, I mean, there were other parallax methods, just geometry, if you will, the Greeks again, that measured the distance to the moon to about a mile, plus or minus a mile. You did 3 orders of magnitude better than that.
Yes, and I think one of the guys in the movie was trying to describe that, but I think we resolved it in some of the initial returns once we found it to like maybe 3, 4, 5 meters or something like that. Subsequently, the McDonald teams able to reduce that just down to 7.
Hal, do you have any idea how accurately this can be done today?
Well, unfortunately, they've terminated the laser ranging experiments now at McDonald. It's all over with now. There was no uproar over it. I was surprised, but I guess after 40 years, somebody said, I was at a conference here just a month ago.
Okay.
And I was speaking, and a gentleman comes to the mic and he says, Hal, what was one of the benefits that you all got from lunar laser ranging? I said, well, one of the things we find is that the moon is traveling away from the Earth at 3 or 4 inches a year. He said, that ain't very much. I said, well, what would it be like when it was coming toward us?
Yeah, but it moves around. It moves away from us at about an inch a year or something.
Yeah, something like that.
Okay, let me get to some of these questions that Brian wanted you to address. The space race and the Cold War were both taking place in the 50s and 60s, of course, Sputnik and then the race into space. But that was also at the time of the civil rights movement,
Yes.
particularly in the South. What sort of prejudices or bigotry did you face, Hal, as a black man working in the high-tech laser industry and traveling on behalf of CORAD and occasionally to the South?
Can we talk frankly in here tonight? I'll start with the story at CORAD, because you have to start where something about that subject came up, my presence as an African American. My management wanted me to take over the role there as the field operations manager. And the first thing, Ted Mayman, the inventor of the laser, said, oh my God, we can't have a black guy going out here representing the laser business. Okay, and the question then was sort of everybody's hand, as I understand, wasn't in the meeting, but said, yeah, that's right, we can't do that. Who's gonna be satisfied that this guy knows enough to talk and do something about this? Black guy, never saw a black guy like that. So of course, as I understand the story, it's written in a book that's been written about this. A dear friend of mine said, guys, are we going to be as prejudiced as the rest of the world right now against black people that we know what hell can do? But the comment came back like this: it's not him that we're worried about, it's what's going to be the effect out there. And wow, that had to be put to a test. So a gentleman who's now, unfortunately, I'll say his name is Rod Waters, a colleague of mine, said, look, why don't Hal and I travel on the next job down south to kind of get a feel for this, okay? Well, the first thing we had to do, anyone here in the movie, here saw the movie Green Book? Yeah. Oh my God, thank goodness. But this will make it easy for me. So yeah, I just saw it, yeah. I said, when we got that all settled, okay, Rod, we'll take a trip down to Savannah, Georgia. Mm-hmm. In 1965 or 6, one of those years. Height of the civil rights movement. So I said to Rod, I was born down there. I can give us some advice. I'm going to do the driving, and you're going to sit in the back, okay? Everybody that saw Green Book, you know why, right? Sure enough, we get to Savannah, Georgia. What our job there was, very quickly, was to put lasers now in those big grain bins and see if we could get the bugs in there to run away or something like that. I can't remember all the details now, but yeah, that was the job. So on the way back, we're nearing Atlanta, going down the highway there, and we're feeling like maybe we better get a sandwich before we get into Atlanta. So I pull into a little shop along the way. Rod quickly jumps out of the car. We're all dressed in our suits and ties. We're nice laser engineers. He runs inside of the little shop, and while I'm sitting there looking, I saw a couple of guys stick their head out the door and kind of survey the area and see me. And I said, uh-oh, because I know that look. I said, uh-oh. Now, I said to Rod, we need a survival mechanism. If I'm not going, if we don't have the fastest car we can find. So we were driving, or whatever the year was, 67, 65 Ford, what's the word? Mustang, thank you. So of course, here comes Rod with the sandwiches in his hand. We jump in the car. I say, let's go, Rod. I put the thing on the floorboard, and we're out of there. And sure enough, after about a few moments down the road, here they come. The guys with the guns in the back window, we all remember them? Here they come. Well, of course, we outran them, thank goodness, but that was our first introduction to things like trouble in the South, being an African American, and even in a mixed relationship, because, of course, who they were really after wasn't me. They were after him, if you know what that means, yeah? And, of course, I would have been the second guy they were after. So when we got clear of that thing, I said to Rod, let's look back home and try to make a big deal out of this to anybody. I know how to handle this sort of stuff in the future. So to make a long story short, I did have a number of incidents across my career in the South. But again, I think when you're trying to get work done and you keep a presence of, I'm here to help, people kind of open doors and back up a little bit. And I'll leave it at that. But it was a very trying time. And my family was sometimes very distressed while I was gone, because it was a time when lots of people were getting hurt in that part of the country. Yeah, I'll take that for. I'll go that far.
Thank you very much, Hal. Got a couple of technical questions here. This is, after all, a technical organization.
Yes.
Ted Myman originally invented the laser at Hughes Research Labs, but he was also working on masers. But Hughes was not interested in lasers. I think masers were invented by Charlie Towns over at Berkeley, right? But they were interested in the masers and not the lasers. Why couldn't they see the light?
Why couldn't they see the light? Boy, this is...
The crowd that was not attracted to begin with is getting ugly.
Hey, that's great. They could not see the light. Well, I think... Howard Hughes, anybody here, well, yeah, okay. Anybody ever, did you ever, no, nobody ever probably met Howard Hughes. I didn't meet him either, I just happened to see him walk by one day. But these guys at Hughes, we were real, we were some pretty tough guys. We built some of the most potent, for example, we built the first air-to-air guided missiles and that sort of stuff. The Phoenix missile was one of those things you could shoot up high into the above an attacking formation and come down through them and detonate nuclear weapons and all that. Oh, wow. But anyway, yeah, so we wanted big bangs for a buck. So when Ted Myman invented the first laser, it had little crystals, maybe about a half-inch long, about a quarter of an inch in diameter, and fired it, and it went. Nobody at Hughes was interested in that at all. So, of course, they said, Ted, you're out of here. As I said, and Ted, of course, went out the door with that reaction to them because, again, he felt that he knew something that was going to be the future, and I thank him for that. And we all want to give Ted Mayman a hand. He really, he could have just folded. He could have just folded and laid down, but he didn't. The guy stood up and said, I'm out of here. You guys ain't going where I'm going. But anyway, I think that the Maser was still, the Hughes was quite interesting. It was a massive machine. Ted had already reduced, I think I'll put a few rough numbers out. Ted had reduced the size of a Maser from something that looked like a refrigerator to something that looked like maybe 2 lunch boxes lined up together. So he had done a great job. A great inventor and innovator was Ted. So Hughes, of course, again, was more interested in the power, and there was no power in a bang, a poop that this laser could make. However, Ted was quite pleased when some of us were able to show that this thing could really do some interesting things, which we did operating from a K-135 out of Albuquerque, where we were shooting down I can't remember the name of the missile air engagements that was operating lasers there also. So I think Ted brought us into the weapons age and into the higher use of technology with lasers.
Okay, well, we could talk about weapons, but let me talk about something else involving high-powered lasers, just to see what you think about it. I mean, this is this guy down at the UC Santa Barbara, am I right, Mike? Phil Lubin, right? Phil Lubin has this idea that, you could send something to the nearest other star and, the lifetime of your average engineer by, putting a little sail on it and sending something the size of a matchbook or something and kicking it with a big laser. Phased up, super duper laser. What do you think of that? I mean, you've been firing lasers at things in the sky.
The power source to generate, well, a couple of things. I was asked to participate in a discussion a few years ago, maybe 4 or 5 years ago, about a similar technology that we could push a 1 gram object to 3/4 the speed of light to get it to Alpha Centauri. Once we did the numbers and started looking at that, we would need probably half the energy on the Earth to get the thing up to speed. Okay, so but we said, wait a minute, that may work if you use light sails and other things, but I'm not sure that we understand how to do things like that yet, and the power sources needed for that. Anybody here that has anything to add to that? That's sort of my feeble opinion, but anybody ever thought about that? Those things like. I know they're poking at it, yeah. But I think I would hope that if they could get a laser beam to acquire that.
Half the power. I mean, this might be the salvation of PG&E.
Okay.
10 cents per kilowatt hour.
Yeah.
Okay. Ted Mayman's original CORAD lasers were based on the use of very small synthetic ruby crystals.
Yes.
Where'd those crystals come from, and how does that relate to a strategic decision by CORAD becoming a division of Union Carbide's Material Systems Division, as they did?
Right, that's right. The first laser, for us that have seen it, of course, is quite an interesting gadget. I'll call it a gadget. And the crystal inside was actually a crystal that Ted, as I understand it, purchased from overseas, from the Switzerland or someplace where you have these rubies made for watches. These guys made these nice rubies. So Ted got one from them. And of course, it was the Towns, and those guys thought they had the idea too. But they reported, I think for all of us that have read the story, Towns reported these types of lasers couldn't be pumped with enough energy to get anything out of them. There was too much inefficiency in these things. Well, somehow Ted got this thing to go, and just like a little poop, a little pip, and it did something. But again, Lindy then came to us and said, hey, look, you're a subsidiary. CORAD was a subsidiary of Union Carbide, right? So they said, look, why don't we team up? So I think that brought together the crystal products. And of course, we were able to work hands in hands. But one thing was very important. We also had a crystal growth lab right at CORAD there in Santa Monica. We had Dr. Pastor and some of the guys there from HRL, Hughes Research Labs, that came along with Ted, that really was starting to look at some very new techniques of, I can't remember all the phrases, the terms used for the methods, Sakrowski, those types of things. But they were starting to experiment with some crystals, and we had a chance to fire those crystals up. And again, we worked hand in hand with Lindy and Union Carbide to actually develop some real efficient ruby crystals. The largest being, if I recollect very quickly, for a laser for the Army, was a amplified multi-stage system that developed a 300 joules, the largest laser we'd ever put together in those days. But it had like a 14 inches long by 3 or 4 inches in diameter crystals. And we took this thing to Fort Monmouth to show it to the Army. They took one look at it, and I swear to God, the guy said, "Don't fire that thing in here." They cut it up into little small pieces and distributed it all over the country to different research labs. But anyway, yeah, Lindy and us worked together.
So these ruby crystals were coming from Switzerland, is that what you said?
The initial one, the initial little guy that Ted got the first little peep out of came from there.
You know, there was a mention earlier about, without actually naming the country, that the first planets around another ordinary star were found by the Swiss, found by astronomers in Switzerland. And I asked one of the guys, why Switzerland? If you think of the countries that do astronomy,
Yeah.
they're all seafaring countries, or
Yeah.
at least were, right? Well, Switzerland, I mean, they don't need navigation from the heavens, so what do they need navigation to cross Lake Geneva? So I asked, I asked this guy, I said, why do you guys even have observatories? And you know what his answer was? The watch industry. Exactly that. He said, you know, we make these really expensive watches, and they needed observatories to make sure the watches actually kept good time.
The accuracy of that.
It's something useful for your next cocktail party.
Yeah, we can use that, yeah, exactly.
Yeah. Okay, during the 50s and the 1960s, a lot of military work was being done by the Americans, obviously the Soviets, and other nations to develop ray guns and death rays. Once again, Buck Rogers, in the hopes of using modern science to fight battles with energy beams. Now, before CORAD was selected for the Apollo 11 Lure science, Lure, L-U-R-E, even though it's laser, what is it? It's, what's the, yeah, lunar laser ranging, that's L-L-R-E, but I guess that's harder to pronounce, yeah.
Back in those days, those guys were so hard.
Okay, all right, in any case, for that project, what were some of the specific applications being developed for the use of weapons-grade lasers to fight against satellites, spy planes, cameras in the sky? You kind of alluded to that.
We had to, you know, the Cold War did play a role with CORAD and along with other companies also. We were the first to build lasers that were used on the battlefield in Vietnam. For example, we built illuminators that were flown in the Pop the Magic Dragon for us, maybe some veterans here from that era. We put a laser illuminators, and one of my guys was actually in Vietnam for about 6 months there operating those lasers from a C-135 or something like that. But we were trying to break up the night operations on the Ho Chi Minh Trail. And so our mission was to go there and just circle the area where of interest was taking place and illuminate that with these lasers from the aircraft. And of course, once we spotted them, and they couldn't see us, of course, we could then bring in the heavy guys that unloaded down there to try to break that up. The Ho Chi Minh Trail became such a factor in both the Cambodia War and in Vietnam, so we put lasers out there to try to disrupt that. I think we were successful as far as the point goes. We all recognize what happened as an outcome of the war, but however, we did present on the battlefield the first laser technologies used in the Vietnam War.
Anything you want to say about the future of space-based laser weaponry?
Someone asked me once.
Maybe you can't say it.
Yeah. Someone asked me once, how did you feel watching Apollo 11 take off? I'll go back there for a moment. I said, I felt like, good, we were just, feeling like we were like dads waiting there for a baby to be born, one of those things. And that feeling, you know what I mean, guys and ladies? Because for us, if that didn't make it, we weren't going to be able to shoot. It would all be down. Well, when I was asked about that, so they said, did you ever have another feeling like that? I said, yeah. It's when our M1 Abram main battle tanks rolled into Baghdad. I was sitting there hoping that the first one wouldn't go down because I had to help develop the fire control system in the thing. So I had to really sit there and say, good heavens, whatever happens, don't let the first one get blown up anyway. No, but I think weapons and lasers and electro-optic systems will become a part of the future. Laser, the debris problem. I think who hasn't here had a thought in your own mind, for example, folks, about how can we solve that? Can you raise your hand if you've had a thought like that? It's a massive problem. If we're encasing ourselves in the world, although there's big gaps in this thing, but we're encasing ourselves now in a real barrier of debris. And you and I know if you get struck by something moving at 18,000, 17,000 miles an hour, it ain't going to be fun. I happen to have a dear friend, Bernard Harris, first African-American to walk in space. He had to actually climb out on the robotic arm when he was on that mission. And of course, his mission was to go out on the arm. He's a physical doctor. Go out on the arm and experience the exposure of the human body to the space and the spacesuits that they had at that particular time. Now, Bernard tells us is one of his lovely stories. He walks out. He's like the arm lifts him out into space from the shuttle bay, and he said immediately his hands felt like they were ice cubes. Now, of course, he wasn't supposed to say, I give up and quick come back. His job was to stay out there until some decisions could be made about the whole apparatus that he was testing. So I'm just trying to say to us that, guys, people have to go out and expose themselves. And, of course, on that mission, their windshield was struck by an object. I will never know exactly what it was, but it nearly penetrated. But he said it was the loudest bang he had ever heard in his life, and he hasn't flown in space since. But that's another story, too. But when we think about lasers in space, death rays, all those kind of things, I think they're coming. We all are aware now that there's a military element of the Space Force? Space Force, so sorry. I was going to say Space Force. I think that a young man at a conference a few weeks ago asked me about Space Force. I said, the military has always been in space. Sputnik was a military satellite. It launched from a military operation. Our guys, von Braun and those guys, put us up. You know, it's always been there. We get excited when we hear about this, but am I right about this? Well, it's always been military. It just wasn't painted with that. But that was the underlying, that was sort of the underlying current of all of that. Well, of course, SpaceX and Elon Musk is a dear friend of mine. Those guys are trying to now put this over into this new arena of capitalism and commercialization. But what's Elon riding on? Technology transfer. He got off the, okay. So I think that we want to recognize that this has always been a part of our technological space adventure. It's military applications relative to use in commercial field. And we'll see more of it. Now, weapons in space, I can't talk about that too much. I'm aware of some things that there's going on now, but they're there.
Al, we want to go to the audience for questions. Before we do, let me ask you just one last question here. And that is, when you're sitting in a restaurant sometime and people find out that you were the guy that fired this laser at the moon, allowed us to measure its precision. I think today the precision is, a couple of millimeters below a millimeter, whatever it is, right? Yeah, it's incredibly accurate. Yeah. And they say, so what?
Yeah.
Right? Who cares? I mean, you're not measuring the distance to Trenton, New Jersey to that accuracy. So why do I care, since I'm going to pay for this kind of stuff, why do I care about measuring the distance to the moon that accurately?
Well, as you all probably know, we experienced a 7.1 recently down in LA. I'm very interested for the guys to continue to use lunar ranging technologies and those things to develop possibly earthquake prediction concepts or methods. So, of course, that's a very personal thing, but I felt a 7.1. It ruined my day. But so I'd like to have us be able to tell us more about those things. That's one benefit. And, of course, I think, too, that light is such a phenomenon that is so yet to learn more about it. For example, when what is light? What's light, guys? Packets, the answer kind of goes all around a lot of places. I think we need to learn more about light. I think we need to learn more about what constitutes that. Dark matter needs to be looked at much more carefully as to what that force is in the universe, things like that. So I see us trying to take those two things and put them together to get more accurate knowledge about the future of our traveling in spaces as spacefaring civilizations.
Terrific.
So Seth and Hal, this is Brian from the back. Just want to make sure there's some details about the experiment that I don't think we've really totally addressed. For example, there's on the screen, we've got 5 students from Wesleyan University who were brought in who
Yeah.
helped with the ranging experiment. This is the actual CORAD laser at Lick Observatory that was used for that. Could you talk a little bit about like working with those students and just the whole process? Because there's a lot that actually went in until you actually made that first measurement.
Well, the first measurement, of course, happened after a number of incidences we've spoken about today while we were there at Lick. One of them was kind of a funny one. We were firing the laser and looking for the initial returns on the first night or two. And of course, we were scratching our heads, why don't we see something? And as we learned later that we weren't timing out because we were maybe 100 meters away from the place that we thought Lick Observatory was. So Joe and those kind of guys sorted that out for us. And that helped us to get a window open so we could finally see the laser pulses. This guy here, I want to raise your hand, Joe, please. Just wave your hand. Joe, those kind of guys made those decisions for us at Lick. I was just a guy on the button to get the beam out, but when all of us were a team together really working to make this happen. But again, the laser's job there was to put a beam out that could, of course, we were running what's called a TEM00 mode, a very tight form diffraction limited type of beam. Because again, when you're trying to fire over that distance, you do not want the beam to get so broken up because you can get that broken spot right over the reflector. You'll never see it. And of course, those types of hot spots that you could possibly develop with a laser like this could also damage the reflector there at the observatory, which again would have been a big no-no. But anyway, what we did, and you can just see the gentleman at the back with the black and white striped shirt on, he's standing in front of the laser rail. That's about a 7-foot rail. And we have the oscillator section back there. That's those 2 devices, blue devices at the back. And that's the oscillator. And of course, we go through some coupling optics there to put the beam up into the amplifier forward here. So we put 5,000 or 6,000 joules into that back section to get about a megawatt of power out of it. And then we push that into this amplifier. We put maybe 10, 20,000 joules into that amplifier to pump that up to 10 or 12 joules of energy output. And this again was coupled into the eyepiece telescope of Joe and those guys did that, and out into the telescope. Now the power supply that I was operating wasn't down in the what we call the basement or the pool. We were up on the main floor, so I could only know something was wrong once I heard a problem happen. But anyway, that did happen a couple of times. So I lost a couple of power supply elements there in a big explosion that shook us all up for a few moments. But when you're discharging that type of energy, it's not a pop that you hear, it's a pretty big bang. So, so we got that fixed and got back in operation within a day or two and went on then to be able to successfully find the reflector, yeah.
What was the size of the spot on the moon once you were using the 120
we were coming from the output of that, the forward blue unit there, that was 3/4 of an inch or so, coupled up to the telescope in the 3 meters and so forth, but at the surface was about a couple of kilometers.
Couple of kilometers, so
yes.
It would be easy to miss the reflector.
Again, I wanted to make that point, if we couldn't keep a very uniform beam. See, my job there was to keep a very uniform beam on the surface. Because if you had a beam that had distortions and those types of issues, then if the reflector could be sitting in one of those, you'll never see it. So that was one of the problems we were trying to keep under control.
Brian, I know that...
There's also one other interesting thing. Can we see the capacitors in this? Because you said it took about a minute for those capacitors to charge up for you to do each. Are those visible in this picture?
Those, we were using, this goes way back to the old days. We were using castor oil fill capacitors. Yeah, a couple of heads shaking here. I think they were rated 5 kilowatts at a couple of something like that. But they were fairly large units, about as big as our monitor there, but they weighed over 100 pounds. They were something like 8 or 10 inches square and about maybe a couple of 3-4 feet tall. And of course they were made a big boom when something went wrong. But it took us 30 to 45 seconds to recharge those, which limited my operating time to just 1 shot per minute. But we could get away with that.
This slide that's up on the screen right now is interesting because this is the official declaration to the International Astronautical Union of the success of the event. And it's my understanding that this was a private telegram that only became public about 5 or 6 weeks ago. And so it's the actual official declaration that, yes, we were successful with this, and it's kind of the declaration to the world of the success. So it has historical relevance.
Thank you. Thank you.
Yeah.
All right. Brian, if you have no objections, I guess we'll go to
Sure.
questions from the audience. So here's your chance. There are some microphones up here, and I assume that they're operational. So if you can come up to the microphone, that will help.
Thank you. I think your story about your adventures in the South would be a great movie. But my question is, given that the MIT receiver blew up and you couldn't use it, how did you actually do the search to find the mirror on the surface of the moon?
That's an interesting question. I was hoping somebody would pick up on that. Thank you. Well,
Pleased to be of help.
What's your name, please?
I'm Nathan Brookwood, Insight 64. I'm an analyst.
Hi, Nathan. Thank you. Once that incident happened, we're at an observatory. And of course, they have visible light. We're running a 60 red light laser. So we went to the observatory, and Irv spoke to a couple of guys there, maybe even Joe. I'm not sure who he spoke to, but he came back to me with a vise in his hand. We went downstairs and took a couple of soldering irons and got into the circuitry and adjusted it so we could change some of the timing elements of it and the time program gain, those types of things, as I remember, a long time ago. But anyway, we modified an observatory device that we then went back and mounted on the device and was able to see the returns for using that. That's my recollection of what we did. Thanks to a lot of help from a lot of guys like Joe and the guys.
How difficult was it to accomplish the alignment between the laser and the telescope optics?
Yeah. The telescope had reflectors around the circumference of it, and if you couldn't get those equally illuminated, you then knew you were off right, off left, things like that. So that was how that was finally manipulated. It took us a little while. In fact, we had to, it's gone, picture's gone. We had to just get that laser head off angle, because as we may want to have you understand, the output beam was not circular. Because of the high energy, high power we were developing, the output had a Brewster angle on it. I can't remember the degree of the number now, but it's set at an angle, so forth, because we wanted to minimize the reflections back into the laser itself. But that meant that the beam wasn't quite centrally located, so we had to kind of offset that to get everything lined up within the telescope, and we did that by hand and watching I think it was the monitors, if I remember correctly.
You mentioned something today about this was proof that there was someone landing on the moon, and I think an astronaut mentioned you or something. Could you repeat that story?
Yeah. For many years, and maybe many of you in the room have run into folk that ask about the waving flag, or why there wasn't a hole in the ground underneath the rocket, and something else I can't remember. But over the past 20 years, I've probably been in 3 dozen conferences where people would bring me up and say, Hal, we got people here want to know about the hoax, of the moon hoax. So I became the guy in LA, if you want to talk about the moon hoax, call Hal, okay? And of course, I would sit there sometimes and I say, my goodness, why don't, because one of the things people would say to me after I gave them this story, they'd say, well, were you on the moon too? I said, no. Well, how do you know they were there? They could have just set the thing up there by whatever and so forth. So I was getting in the box about this thing. I said, well, because they were looking for a while, there wasn't a hole in the ground and the flag. You know. Finally, I said, why doesn't Neil Armstrong say something? Because I was getting nervous myself about this, okay? So finally, the only time I think I ever read, Neil Armstrong recorded this statement. Anybody that doesn't believe that we went to the moon, look at the laser ranging experiment. There's the evidence. So I started using that.
Yeah, but didn't the Russians have a retro rocket? They didn't go to the moon.
Well, they certainly...
They had a retro reflector.
Well, yeah. They had a reflector. Of course, as I mentioned, their reflector, their device got into a crater.
Into a ditch.
Into a ditch. I use the word ditch, but yeah, okay. They couldn't get their mirror. Anyway, yeah, but later found it and showed where it was, yeah.
Yeah. The detector technology of the time, the photomultipliers, you're
Yes.
talking only 3 photons. How, how good were the photomultipliers, and how did you integrate all of that and actually get a nice signal out of the system?
I'll have to give that answer to, like this. I mean, this is nearly like I was talking about the other subjects you bring up sometime. You don't quite have the total picture. What we were trying to do is come up with a visible light detecting system that would allow us to be able to at least look for these returns. Because again, the device that MIT had built for us was specifically just constructed and designed to look for those 3 or 4, and that was their gain profile, so forth and so on, to make that work. Now, Irv, who again I mention his name quite often, he's now deceased, but Irv was a very good electrical engineer besides being a physicist. We took the device downstairs, and I couldn't walk down today. I was sure going to hope to try to do that to where he and I got with the soldering irons and the electronics and fixed it. I wanted to get under the stairway there, but I got afraid I couldn't get back out. But anyway, we made some adjustments on it, and I'm sure that between he and I what we did with the electronics, along with the other technology from the folk at LIC, were able to be put into a conversation that eventually gave us what we needed to get that done. Evidence, it worked.
I mean, that has to be pretty fast electronics, right?
Yes.
I mean, with a foot per nanosecond and there and back and all of it.
I can't resist making a couple of comments. The guy in the white shirt there is Barry Turnrose, who, Seth, you may remember. And his job was to give me offset coordinates from lunar craters for where the retroreflector might be. But we also did a raster scan.
Yes.
Now, the telescope on the front spiders had 2 retroreflectors that were very accurately made. So we knew that the beam from them came directly back onto the telescope and finally to a guiding eyepiece. There were 2 mirrors like this. The first mirror was coated to reflect the laser light. So the laser light came up off of that mirror into the telescope. But it was transparent to optical light, which went to the second mirror and down to a TV guider. And my job was to look at where the splash caused by the retroreflectors on the telescope landed on the moon. And I moved that splot around to the right position. And Walter Cronkite said that that splot that came from the telescope was from the moon on the first night.
Now, for those, Joe, thank you for that. I think you heard it from the expert. Thanks a lot, Joe, for that. I always love it when there's somebody in the audience that was there to help us. Now, for us that are old enough to remember, in the days news of fake news, remember fake news? Walter had the notoriety of the. Can everyone remind me what he was called? Anyway, he was the truth of the news. Most trusted man in America. Now, Walter Joe and I were talking about this earlier. Walter had been told, well, how are we going to know when we fired the laser into the moon? And so he was told that you're going to notice some little spots on those reflectors, retroreflectors that Joe just mentioned. So he's sitting up there wherever he is in CBS or ABC, whatever it was. And so he announces, because he saw these spots, that something already had gone to the moon and we got in it back. We were all scratching our heads. Hold it, Walter. That isn't the answer yet.
Let me make one more comment. When we got the returns from the moon, we could move off the position where we thought the retroreflector was, and then we got nothing. And then we moved it back onto the retroreflector, and we got returns.
Yes.
But more than that, over the night, we noticed a drift. So instead, we had a projected orbit for the moon, and we were expecting all of the returns to line up at, say, 0 coordinate. But it wasn't. It was slanted. And we scratched our head. How did we get this slant in there? Because it was too much. We knew too much about the orbit of the moon to have that big an error in the knowledge of the orbit. And then it hit us. Where is the telescope? The telescope was not at the position of Lick Observatory. The telescope was at the position where the telescope was. Lick Observatory was at the main building. And when you calculate the distance and the fact that the moon is setting and increasing that distance, that accounted for the drift. So something we were not expecting, we saw, and only afterwards did we understand it. So there is no way that that reflector was not on the moon.
Joe, if you don't mind, I think everyone's count, maybe that they're not aware of who you are. Could you just sort of give who you are in this role that you had there in the Apollo, in the lunar mission? Tell us a little bit about who you are and your relationship. You're the expert here now to helping me.
I didn't come here to give a speech.
Okay, well, all right, we'll leave you out of that.
But at least tell everybody your name, Joe.
Yes. See, there's folk in the audience that were on this team.
Okay, I'm Joe Wampler, and at the time I was an assistant professor at the University of California, Santa Cruz. And Jim Fowler and I were in charge of the laser experiment at Santa Cruz. And let me just say one other thing. Jim and I have been in contact, and he feels that if we had not acquired the retroreflector, that NASA would have cut the funding for it, because the astronauts had already left. NASA felt that there was a real danger the retroreflector would be covered. And so there was a real, and McDonald was not acquiring it. In fact, McDonald didn't acquire it until about a month after we acquired it. And that was probably a long enough delay that NASA would have cut the funding. So the contribution of Lick was we found it, we told everybody where it was, and we knew that the orbit of the moon that Mulholland had calculated at JPL was a reasonably good orbit.
Thank you, Joe. Thank you, Joe. Everybody, I just want you to know who this guy was. All right.
All right, last chance.
Up on the screen right now is a description. Oh, I don't think somebody's at the mic yet. So here's a description of actually how it works. We haven't actually gone through these steps. So do you want to talk through this slide?
We were just, this is just letting us describing how it worked. We've heard the discussion about the mechanics and things of the lasers and so forth. But again, the average distance we were able to record was something like 385. I think around 385. The dispersion caused the lasers being the footprint to be about 7K at the diameter when they reached the moon, and 20K on the reflected return to us on the Earth. That's why, again, the very important job I had was to maintain a very uniform beam out of this laser under some very sophisticated troubling issues that we were having with the pumping of the laser. And again, typically we were running a TEM, those that may be familiar with how lasers are set up. We were trying to run a TEM00 beam, but for that purpose. Next one.
Well, just so it's clear, because we haven't actually talked about what a retroreflector is. There might be some people.
Now, retroreflectors, now in this particular case, Dr. Lassie, excuse me for forgetting his name right now, developed this retroreflector, if I'm not correct on that, Joe. But anyway, the retroreflector that we were using, the characteristics of it was the black lines, where it comes in from the source and returns directly toward it, rather than taking an object course, for example, an incident of normal reflectors that would send it off at some other angle. So this allowed us to collect maximum energy back from the retroreflector directly to us here on the surface. So that was the key to making this work, not so much the laser power, but the fact that the reflector was sent back in a line of sight directly toward us from the object there on the ground. Okay?
Right, and I think there's a set of even like, something like 100
Oh, by the
mirrors.
way, and of course, in that unit, there are 100 rectal reflectors with an aperture of about approximately a couple of centimeters in diameter.
And just for sake of context, here is the actual telescope in the dome of the building, and then the laser itself was actually in the basement. So it was wired up so that it would end up going into the through the telescope. And I think part of the reason it was in the basement is because there's such a danger of maybe a fire or explosion. They wanted to make sure that if they had to douse it with water, that it would be minimal what the impact would be. Is that a pretty accurate statement?
I didn't think so, but maybe somebody else thought so.
That's what I heard at least.
My laser was not going to get into that type of trouble.
Okay, you hope.
But
Right,
yeah, okay.
right.
Now, you can go back there for a minute to the past. I want to point out, there's Buzz and I have been together for years at seminars like this and talks like this. And of course, he's a great guy, but if you mention anything about the hoax, he punches you.
I heard the fellow that he punched famously on that video
Yeah.
was on the radio 2 nights ago.
Yeah.
And somebody asked him about the reflector on the moon as proof that we had gone there. And he said, no, that's not true. They were just aiming the lasers at the surface of the moon where it was bright and would reflect a lot.
Oh. Well, I got to speak to Buzz about that next time I see him. Okay. Well, the drop down, of course, I described a little bit of my work at Hughes Aircraft Company. We use lasers, integrated lasers into main battle tank fire control systems in the early 70s. The M1 Abrams, which many of us see in action now in the Middle East War, we developed that fire control system. But again, our problem, and I might mention this very quickly, one of the reasons why we needed to bring lasers to the battlefield, at least in the armored systems, is because the Russians outnumbered us nearly something like 100 to 1 or whatever, some large number like that in armor. Well, when we were thinking about a fight in West Germany with these guys coming through what was called a Folder Gap, we had to have a tank that could shoot on the run. And I spent probably just hundreds of hours down in White Sands, New Mexico, riding in the M1, testing and developing in the development phase of the lasers used in there for ranging. Now, one of the big problems I had initially, once we got the system working, the old tankers who were used to doing the parallax fire control systems, when they saw the laser, you push a button and the range comes back 1,200 meters. They would say, how do you really know that that's the truth? I say, well, if you wait to check it, you'll be dead. How about that? So anyway, we finally got those guys to come into the tanks with us and ride and look at the targets and do multiple sensors, let them know the range was true. Finally now, I guess we've all seen these actions. Those tanks are really doing a great job. Now, the other thing we did again is brought directed energy warfare systems to the table. We, of course, one of the systems we worked on did get banned by the, what's it called, the Geneva Convention. So that's the system I'd love to tell you about, but it's classified still yet today. But again, we have lasers in space, of course, now mostly in communications tasks. But again, the military are looking, of course, to use lasers in some weapon technologies. Yeah.
Thank you very much, Seth and Hal.
Yeah. Enjoy.
So because this is an IEEE milestone dedication, I'm going to read the citation of the plaque. So this plaque is mounted in the lobby of the Shane telescope. That's the 120-inch telescope at Lick Observatory. There, you often see from down here, you see a really big dome. That's the old telescope that isn't used much anymore. So the main telescope is the Shane telescope, and the words of that plaque read as follows. On 1 August 1969, Lick Observatory made the first Earth-to-Moon distance measurement with centimeter accuracy. The researchers fired a gigawatt ruby laser at a retroreflector array placed on the moon by Apollo 11 astronauts and measured the time delay in detecting the reflected pulse. This was the first experiment using the hand-placed extraterrestrial instrument. That's the milestone. Now, Brian Haggerty, do you have that other plaque? I do. Yeah, would you like to read that? There's actually going to be a second plaque installed in the lobby. The reason for that is because generally with IEEE milestones, they don't actually name people. They're neutral on that. But to recognize all the people who were involved with this, Brian Haggerty, who's from Southern California, IEEE officer down there, he was the one who told me about his plan for this milestone. So I carried this through, but he wanted to make sure that the people who actually were part of the milestone or the Lure effort were included. And so there'll be a plaque mounted in the Shane lobby. There'll also be another plaque given to the UC Santa Cruz. It'll be in Santa Cruz in a more publicly accessible location. Could you read the words from that plaque, please, Brian?
So I'm the chair of IEEE Southern California Council, and I've been working with Hal and Betty Walker close to 10 years now, I think, and I'm also a member of the International Optical Society. In the year 2016 was the 100th anniversary of the Optical Society, and we wrote a feature-length article about Hal's work and his life's work. So that's really how I got involved with, Brian Berg and a lot of others. Likewise, the city of Santa Monica, which is the home of Corad Lasers, is doing a similar set of events, just as LIC would do here. So we actually today provided one of these plaques. This is the second one for LIC Observatory and one for UC Santa Cruz. We have a similar set of plaques down in Santa Monica, which is celebrating their 250th anniversary as a city, as a Spanish encampment. Anyway, so this is the plaque that really honors the people that were involved. And I'll just read, I'm going to read the second half because the first half is basically what you see up there about the event itself. It says, presented 1st August 2019 to UC Santa Cruz and LIC Observatory in commemoration of the Apollo 11 lunar laser ranging experiment. The next paragraph is pretty much what you see on the milestone up there. But then the second paragraph says about the people involved. Science and engineering teams from LIC Observatory and Corad Lasers were jointly responsible for the success of the lunar laser ranging experiment known as LURE. Planning began more than a year earlier with the Corad team led by Ted Maiman, the inventor of the laser, Bill Rundle, the designer, and Hildreth Hal Walker Jr., who installed, operated, and fired the laser from LIC Observatory in July and August of 1969. The team responsible for operating the telescope, precision targeting of the retroreflectors, and performing the electronic data collection and measurements was led by James Fowler and Irv Weiner of Wesleyan University, and Lloyd Robinson and Joseph Wampler, and Donald Weber of LIC Observatory. So we have a pair of these. One goes to LIC Observatory and one goes to UC Santa Cruz. And really it's Hal Walker's presenting this to the observatory, so I'll leave it with you because we presented it to Eleanor earlier today, but you can deliver that to Santa Cruz.
Thank you, Brian.
You bet.
And thank you all for coming tonight. Have a good evening.
Thank you so much. It was a lot of fun.